Hey everyone, so today is our first of two classes where we're going to be looking at descriptive stats. So we've already started with our descriptive data when in terms of looking at kind of data visualization, so how we can visualize our data set and learn a lot from, from our raw data and transforming it into a table or into a graph that does a better job of kind of providing us information about our data, kind of the pattern of data. Today, we're going to be looking at measures of location as kind of more formal stats that provides us with a statistic itself, not a graph or a table, but an individual statistic that can summarize a wide set of data. And then the next time we'll be looking at measures of location. For the recorded video, when we get the problems, I'll have a very brief pause, but I'm not going to wait long before going to the solution. So I'd encourage you still to do all the calculations, try out the problems yourself, so just hit pause when we get to one of the problems, give it a try yourself. And once you're done, just hit play and continue on and see if you had the right solution. All right, so just a couple, since this is one of the first times that we're dealing directly with statistics, just a couple of more housekeeping notes in terms of how to deal with numbers. So first, a note on rounding. So when you're doing calculations, how should you be rounding? So state your answers with one more decimal place of precision than is found in the raw data, only when it makes sense. So for example, if we're taking the mean of 2, 3, and 5, well, that, if we put into a calculator, is 3.33 repeated for a long time, indefinitely. And that, we need some point where we can cut that off, right? We can't write an infinite number of 3s going forward. So in this case, we'd go to one further decimal place than what the raw data had, and the raw data stopped at the whole number, so 2 point nothing, nothing in the 10th position. So we'd go and just have one decimal place further, we'd round to 3.3. Because the raw data are whole numbers, we round to the nearest 10th. As always, round only the final answer and not any intermediate value used in your calculation. So usually we would follow the rounding rule only at the end, but we would try to keep as close to the true number, unrounded numbers in each of the intermediary steps. So not round, say, to 3.3. If we're doing further steps later, keep 3.3 repeated when doing further calculations. We also, with a lot of these different techniques, we're going to be using some mathematical formula. So I'm going to try, whenever we're using formula, to describe it as well as possible in words. But oftentimes in books or in articles or things like that, you're going to see it listed in mathematical notation. So having an understanding of what the mathematical notation means will make your life a lot easier. Also, for those of you who are more mathematically inclined, it's a much quicker way to convey information than, say, verbally or in text where you're describing it. So you can, in a much smaller amount of space, convey a lot of information, a lot more information when you're using mathematical notation. So I'm going to, as much as possible, try to use the full mathematical and correct mathematical notation on our slides. But I'll talk through, for those who don't particularly like that type of notation, I'll try to also talk through what we're doing. So first, in terms of summation, imagine that we had the numeric grades for 15 students. So 15 students wrote a test and we've got their numeric grades. If the first student got a 75, we typically would write this as X sub 1. So subscript 1 is equal to 75. So we're using X here as just noting kind of an observation. So a point of observation. So one student, rather than say putting their name or ID number, we're referring to each student as X. It doesn't have to be X. Commonly we use X, but say we were looking at two classes, one class we might be using X and another one we might be using Y. There's no particular reason it has to be X, it's just the most commonly used. And so for the first observation, we would say X sub 1. And so we would say X sub 1 or is equal to 75, or X1 is equal to 75. The second student got a 93, we would write this as X subscript 2, or X2 is equal to 93. And the score for the 15 students are represented by X1 through X15. 15 students, so X1, X2, X3, X4, X5, through X15, so the last one being the 15th student. So that's just if you start seeing like X x3, that means we're talking about the third observation. If you see x7, that means we're talking about the seventh observation. And then you could look in through your list of observations and grab that particular one. The notation xi, or x subscript I, is used to represent the ith student. So say we're just trying to talk in general terms that there's going to be a particular observation. So not all observations, but we're going to be selecting a particular observation, but we don't necessarily know in advance which one. Like, it's just referring to one individual non-specific observation. Because if we're saying X, we could be talking about the full data set, right? The full list of 15 observations. So we need a way of indicating we're not talking about all 15, but one particular one. So XI would be the ith student, where we would fill in I depending on the context. And the sample size is written by n, and that's generally the case almost always. So x can change across context, right? There's no particular rule. It has to be x, where it's more conventional, where sample size is pretty much always written by n. And so sample size is written by n. So with 15 students, xn is equal to x15. So if you say xn, it means the last observation. So in our particular case, we are talking about 15 students. So the last observation is the 15th student. So xn sample size is equal to x15. So 15 students. If we had 30 students, xn would be equal to x30, so on and so forth. The summation notation is just a shorthand way of indicating that observations x1 through xn, so the first observation through the last observation, are to be summed, right? But rather than writing x1 plus x2 plus x3 plus x4 plus x5 plus x6 plus x7, so on and so forth, even with 10 observations, that would take a while. If you're talking about, a million observations, that would be completely unwieldy. So we need a way of shortening it. Now you can use, like we have on the, the right side of the, hang on, I just want it. On the right side of the equal sign here, right? You could just do x1 plus x2 plus ... through xn. That's one way of simplifying a long series, but it's not particularly elegant. The simplest way is we're using the summation notation is using the capital Greek sigma letter. And so we're saying the sum of all xi observations, right? So we're saying x, so x, remember, I is taking any individual observation. And we're saying is we're summing observations within the data set x. And so the I is equal to 1, and the n here indicates the range of summation. So, so in this case, we're saying sum all observations of x from the first one through to the last one. So this is where you start. This is where you end. So in this case, we're saying from the first observation to the last observation, sum or add up all of the observations of x. So the I equals 1 and n indicate the range of summation. If, for example, you only want to add the observations 2 through 5, you'd replace I equals 1 with I is equal to 2 and replace n with 5. So say we just cared about the second, third, fourth, and fifth student, and we wanted to add up their scores, right? We would have I is equal to 2, we'd have 5 up here, and then we'd know, okay, we only add up those observations that meet those criteria. So we'd add up the scores for the second, third, fourth, and fifth students. If, and this will often be the case, if you're summing all the observations, it's acceptable to omit the index of summation. So the index of summation being the I is equal to 1 in the end. If you just see like the sigma symbol with like xi or with x, really that's just telling you add up all observations with an x. So by shorthand, if everything's been included, you don't have to put the 1 through n. And that's typically, like I said, going to be the case. So most of the time, that's the way you'll see it with summation. So rather than listing a whole long list here of x and doing x1 plus x2 plus x3, all this short, fairly simple symbol tells you to add up the full, all the different observations within your data set x. All right, so now that we've got a little bit of the symbols, and we'll talk through the symbols if we see them again, explaining what the different formula mean. We'll start in with measures of location, which are the descriptive statistics that we'll be covering today. At least some of them. There's many different measures of location. We're only going to be looking at a few in this particular course. So a measure of location is a common definition of measure of location is that it's a number intended to reflect the typical individual or thing under study, right? So we want a way of, we've got like all these different observations, right? And we want a way to convey to someone, you know, if we had to say, what is the typical, what is the average observation within this data set, and convey, okay, well, you know, you can understand this data set, all these different observations best by, or well, by looking at what is the typical observation within it. And so a measure of location is any measurement or any statistic that reflects the typical individual, that tells you, okay, this is what the typical individual is within this data set. There's a variety of different ways that you can do it, but each of them, that is the goal, is to they tell you kind of, you know, this is the average individual within, or average object thing under study. So the mean is the most typical uh, uh, measure of location that you'll see. It's what we most typically, when you think about average, when people say like, what is the average in something, what they actually usually mean is the mean. So when we say like the average, or if you say average, average is actually a series of different statistics. So it's not really a precise word. There's a variety of different things that could fit as the average. The one that we most commonly mean when we say like, what average did people get on tests? You know, what was the class average on quiz 1? What was the class average on quiz 2? What's the average height of students? What we typically actually mean is, or we're trying to usually represent, is what is the mean grade? What is the mean height? So when we're dealing with a population, so all members of the class, say, and that's our population under study, we use the symbol mu. So this symbol here we use to represent the population mean. So if we're talking about the mean and we're looking at a population, we'd say mu, or we'd say this symbol, we'd use it to represent the mean. When we're dealing with a sample, we use the symbol X bar to represent the sample mean. So it's red X bar. Since we more commonly use samples in the social sciences, we'll generally use X bar. So again, this is, remember when I talked about earlier in the class, I said, understand the difference between sample and population is important because this difference can lead to mistakes. In the case of the mean, it's not a particularly big deal. The formula for doing the population mean and for doing the sample mean is the same. So it's not going to lead to a huge mistake if you misinterpret whether something's a sample or the population, but you are going to use the wrong symbol for showing your work and for showing what you're doing, which can lead to confusion and lead to mistakes. In some of the things we'll see later when we're looking at, say, measures of dispersion next time, which is another type of descriptive statistics, the difference between population statistics and sample statistics will be more significant in that you're not only going to have the wrong symbol showing what you did, but you're also going to have the wrong answer. So starting to get used to identifying whether something's a sample or a population is important. So the mean is what we, like I said, it's what we most commonly refer to as the average value. And it's found as follows. So the mean is equal to sum of all values. So we add up all the different values or all the different observations that we have. And we divide it by the total number of values. So the sample size or the population size that we would be going with. So more formally, so to simplify it from words into kind of mathematical notation, X bar, so our sample mean, is equal to the sum of all observations, right? So all individual observations divided by the sample size. So that is translating essentially, this is translating this. So sum of all observations, sum of all values, total number of values, sample size. Total number of values is in the sample is the same thing as the sample size. If it was population, we'd have mu. We'd still have sum of all xi divided by n, but we'd be talking about, rather than the sample size, we'd be talking about the population size. So the big difference would be a change to just the symbol here. So this is, again, a simpler set of notation than having to write this out. It takes a lot less room, and it conveys all the information, the exact same information, just in terms of symbols. So we take all the different observations that we have, say 15 students, all the 15 scores, we add them up and we divide them by 15, which was the number of observations that we had from the example that we started with at the beginning. So let's give it a try. So 8 grocery stores sell the PR energy bar for the following prices. So here are the different prices, and find the mean for these prices. And assume that 8 grocery stores or other grocery stores that sell this bar as well. So pause it, give it a try, calculate what the mean is, and when you're done, hit play again, and we'll take a look together. So the solution, the mean price is $1.41. And so remember, so we add up all the different individual observations. So $1.09, plus $1.29, plus $1.29, plus $1.35, $1.39, so on and so forth. And we had 8 different stores, so we divide by the sample size, which was 8. And that gives us all of this added up, divided by 8, gives us $1.41. Sample mean can also be used, calculated using relative frequencies, which we saw last time. And so in terms of notation, the notation f of x indicates, or f sub x, or fx indicates the number of times the value x occurs in the sample. So f here is referring to frequency, so relative frequencies. So the relative frequency of x can be represented as the frequency of x divided by the sample size, right? So remember, relative frequency is how often something occurs divided by the sample size. So if a particular observation happens 10 times, or a particular score happens 10 times out of 15 students, that would be, the relative frequency would be 10 out of 15. And so same calculations as we've seen before for figuring out relative frequency. But if we have the relative frequency, we can simplify somewhat the calculation of the mean. It's really actually doing the same thing, but it could be simplified somewhat. So the sample mean then becomes, the sample mean is equal to, so here the sum for x. So each x times its frequency divided by n. So for each observation, we would multiply it by its frequency. We'd sum that up for all different observations, and then we divide it by the sample size. And so, in this way, we could be getting the mean through the same process, a slightly different formula, but it gives the same end result. And we'll see in a second why this can be more useful. So you take, say some people got 75% on a test. So we take, okay, and some people got 80 and some people got 85. So we take, okay, so the first observation is 75. So we take 75 times the number of people who got 75. And then we take 8 plus 80 times the number of people who got 80 plus 85 times the number of people who got 85 divided by the entire sample size. So let's give this a try. So for the following frequency table, calculate the sample mean. So here's some scores. Here's some frequencies. Here's the total. So try using, you could try both methods if you want. So the original method that we did, where you sum up each observation and then divide by the entire sample size. But definitely try it with the relative frequency method, and we'll take a look at what the difference is. So pause it, give it a try, and then we'll come back together. All right, so here's the solution. So here's kind of the simple summation version that we did before, right? We take all the different scores. So two we saw before, two people got 59, so we got 59 plus 59, and then four people got 72, so plus 72, plus 72, plus 72, plus 72, so on and so forth through the end of it. We had 15 different observations, and so we use this. This is pretty practical. There's nothing wrong with this. But with a really large data set, particularly if you're doing it by hand, it can, take a while. So imagine we were dealing, instead of 15 observations, we had 200 people in the class, and you had to add up each individual score and then divide it by 200. It would take a while to add up each of those individual ones. Where now, if the scores don't repeat, that's what we're going to have to do. So if it's, one person got 51.1, somebody got 51.3, someone got 51.7, someone got 51.9. And so each different person of, say, the 200 got a different score. That's what we'd have to go with. But when you've got repeating numbers like we have here, right, you can actually save a lot of time, particularly as the data set gets bigger, by doing it this way, right? So we have two people who got, so we've got, some people got 59. So we've got 59 times the relative frequency of that, plus 72 times the relative frequency, plus 75 times the relative frequency, plus 83 times the relative frequency, plus so on and so forth, all the way until the end. And it gives us, in either case, it gives us 74.2. So whichever way you do it, it's not going to make a difference. So it's just in terms of, if you got a lot of repeated ones, this could be quicker. So 59 times 2 over 15 plus 72 times 4 over 15 plus 75 times its relative frequency plus 83 times its relative frequency. This will give us the exact same thing as this will. So the mean has a lot of advantages, right? Like, it's easy to understand. It uses all the data. It's something that most people, when they think about most typical value, their mind's automatically going to go to the mean, right? Like, we intuitively think when we want to, say, summarize different observations, we automatically go to, what was the average score on this test? What was the average height of members of a different basketball team? What was the average speed of cars in a particular location? To signify typical value, the mean is what most people think about. So it has a lot of advantages that, in that sense. Also, in terms of some of the more advanced statistics that we're going to be using later, the mean serves as a foundation piece for a lot of the formula that we're going to be using later for doing more complex things are relying on the mean. So it's really useful in terms of building up other statistics, more advanced statistics. And when those more advanced statistics are based on the mean, they're also usually the ones that are most easy to understand. So there's a lot of advantages from a practicality and from, I guess, like an intuitive understanding perspective to using the mean. Where the mean runs into some problems is in terms of what we refer to as a sample breakdown point, or in terms of outliers. So an outlier is an unusually large or small value within your data set. So you say you've got your flow of data, you've got your observations on like your scores on a test, and if you've got one or more values that is just distinctly different from the other ones. So imagine a test on a test, and everybody studied pretty well. So everybody got between 75 and 95 on the test, but one person just didn't study at all, and so they got 10%. Right, that is vastly different than what everyone else did, or nobody studied. Right, everybody was I don't know, watching sports, or watching a movie, or at a Champlain party the night before, and so nobody studied except for one person. So everybody flunked the test except one person studied really well, and they got 95. Right, so that one person is vastly different from everyone else. We'd call those scores that are unusually large or small, we call them as outliers. And so the sample breakdown point, or the finite sample breakdown point, is the smallest proportion of observations that can make a measure of location arbitrarily large or small. So essentially, how many observations need to be outliers for a measure of location to become essentially meaningless, where it no longer reflects what we would think of as, the typical value within a data set. And this is where the mean can run into some fairly significant problems. So for the sample mean, a single outlier can make the mean arbitrarily large or small. So we'd refer to as the finite sample breakdown point for the mean is 1 over n, right? So the proportion of observations that can make it arbitrarily large or small. In this particular case, it's 1 over whatever the sample size is. But more simply, it's just a single point can have that effect. And so that's a major problem. Just one observation, if it could throw off your entire data set, or sorry, your entire statistic to make it essentially meaningless, or at least quite arbitrary. That's, in the real world, we often have outliers, right? We often have unusual observations. So that is a vulnerability. That's a potential problem when it comes to the mean. It's also a potential problem to any more advanced statistic that relies on the mean. Because, like I've said before, if you put garbage into your calculations, it doesn't matter what formula you're using. If you put garbage in, you're getting garbage out. If the mean is essentially garbage because it's meaningless because it's made arbitrarily large or small, and you put it into a more advanced calculation, you're putting garbage data in, you're going to get garbage out. So let's see exactly what the problem is. So let's look at these two data sets to calculate the mean for the following sets of values. So we've got sample 1, 1 through 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and sample 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 1 million. So notice in both of these different data sets, there are 10 observations, so they have the same sample size or population size. It doesn't particularly matter in this case. And 9 of the 10 observations are exactly the same, right? Both of them have a 1, both have 2, both have 3, both have 4, all the way up through 9, the same. The only difference is, one ends with 10, one ends with 1 million. The 1 million is the one that we'd look and say, okay, this doesn't seem to fit the sequence. Now, what does it do to the mean? So calculate the mean for both, pause and come back, and we'll take a look. Good practice for calculating the mean as well. So for the sample 1, where is 1 through 10, the sample mean is 5.5, right? And if we look at the data set, I think that does a pretty good job of representing, if we want to be summarizing 1 through 10, where each observation is there and what's the typical value, I think 5.5 does a pretty decent job of doing that. For sample 2, the mean is 100,004.5, right? And if we go and look at 1, 2, 3, 4, 5, 6, 7, 8, 9, and 1 million, 100,004.5 doesn't seem to do a particularly job of representing any of that. There's none of the values. If it's representing the typical value, none of the values are even remotely close to this number, right? Like the 1 through 9 are all about 100,000 less than approximately 100,000 less than what the mean is, and the highest one, the million, is about 900,000 away. So if we showed to somebody this data 1 through 9 and 1 million, the typical value, even though that 1 million seems to be right out there, if we wanted to say what we'd expect. Think about it. If we said, okay, we add an 11th observation, or another person comes in, what would we expect them to have? We'd expect them probably to have somewhere in the 1 through 9 range, not near 100,000, right? In sample 1, we'd say, okay, if another person came in, not saying adding to the sequence, but like there's a certain rule that gave us this, we'd probably expect another person, they'd probably be around 5.5, right? Typical value, that makes sense. And so if these were scores that people had on a test where you get 1 through 10, we would expect the next person probably get like 5.5. Say there's a test where you could get scores 1 through 1 million upon it, right? And an 11th person came and took the test. Well, based on this pattern, we'd probably expect the person again to get somewhere in the 5.5 range, maybe a little higher, right? Because there are a whole bunch of other possibilities. Clearly, it goes all the way up to 1 million. Someone did super well, so maybe a little bit higher than 5.5. But given that the vast majority of the people were in this range, we'd probably expect the next person to be somewhere in that range, a little bit higher than here, but still somewhere in that range. That would indicate, well, the typical value. So the mean here becomes almost meaningless, right? And so that is a vulnerability, like I said, to the mean, because one outlier, right, one extreme value can make it where, you know, you look at the mean and it doesn't seem to convey much information. So there's a variety of things that we can try to do, given that outliers are fairly typical in our data, right? It's often good, particularly if you have a data set of a sufficient size, having an outlier is not particularly unusual. If, to be honest, it's not only not particularly unusual, it's fairly common. We need ways that we could possibly deal with it. So try to come up with techniques that still capture the typical value, but that are less sensitive to outliers. And so given that a single extreme value can result in a sample mean that poorly reflects the typical response, a variety of techniques have been developed to deal with this problem. One group of techniques involves simply trimming the smallest and largest values and averaging the remaining values. So in other words, imagine we arranged all of our data in order from smallest to largest. By definition, the most unusual values, the ones that were arbitrarily small or large, would be either the smallest or the largest values in the data set. So trimming essentially operates by, let's remove the smallest or largest, not necessarily saying that they're necessarily outliers. We probably don't know if they are. We might not know if they are, particularly within the sample context. We don't know if they're outliers. So we would take the technique of just, we drop the smallest and we drop the largest ones. And we then take the average of the remaining values. So here, there is a clear disadvantage, right? We're dropping data. Anytime you're dropping observations, right, you're not drawing your conclusions from your full set of data, and so you're losing something, right? So all else being equal, if your data does not have outliers, the mean is the superior, for many reasons, is the superior measure of location, right? It's easy to understand. It goes into a lot of formulas. It's easy to calculate, and it does not drop data. And we don't like dropping data, right? We like making our calculations based on our full data set. So by dropping some data, trimming always involves a sacrifice. But given how there's always that cost benefit analysis, right? Like if outliers are present or possibly present, can we use the mean? So we often commonly do, but it is certainly a concern. And so the median, but you've probably already seen the median before in math classes you've taken before, is the best known technique to employ trimming. We often don't think of when the median's taught. It's not often portrayed as a trimming technique. It's just, we've got the mean and we've got the median, and maybe you've seen the mode before, right? And so we've got these three different techniques, but really actually the median is kind of a calculation of the mean, just with the highest level of trimming pretty much possible. And so essentially it is still another way of calculating the mean, just with certain values trimmed. So the median is the middle value in the sorted data set. So essentially it's the mid, if you put, so when you calculate the mean, you don't have to, you could just take your data and you don't have to put them in order from smallest to largest. When you're calculating the median, you always have to start by putting your data in the order from the smallest to largest. And then essentially the median is the middle value. So it's a halfway point, or the halfway point between the two middle values if the number of values is even. So it's your middle data point. So in terms of what is a typical value, well, the middle, we typically think middle is typical value. So it makes a lot of intuitive sense. Where again the median loses out is you're dropping a lot of values, right? So it may not reflect particularly well kind of the shape of your data, right? Like there could be a lot of clustering far away from the center, and then you've got kind of the middle values. It could be like, there's like 10 observations of 10. Say you've got like 20 different observations. You've got like 10 observations or 11 observations that are all 10. And then you've got like 20, 30, 40, 50, 60, 70, 80, 90, or your other ones kind of going out. The median would be 10 because it's the middle of that sequence if we put in numeric order. But in terms of thinking about like what number best represents this data set, it's missing a lot of detail about what's going on past that middle point or on one side of the middle point. And so if we had looked at, say, just the data, so 10, 10, 10, 11 times, and then 9 more numbers that are 20, 30, 40, 50, 60, 70, 80, so on and so forth, right? If we had looked at that and said what was the typical value, 10 is probably not what we would have chosen. It's the most common. It's the middle one, but it doesn't necessarily reflect the pattern that we're seeing in observations. So it has a lot of advantages, but it also has certain disadvantages. So to calculate the median, so like I said, we have to take all of our different observations, so x1 through xn, and we have to put them in numeric order. So in kind of mathematical speak, let x1 in parentheses represent the smallest number, and xn in parentheses represent the largest number, and then organize the observations so that they're essentially in numeric order. So x1 in parentheses is smaller than x2 in parentheses is smaller than x3 in parentheses is smaller than x4, so on, all the way up to xn. So essentially, like I said, this is indicating that when we're dealing with the median, unlike the mean, when we're dealing with the median, your starting point, the first thing you have to always do is put your numbers, your observations in order from smallest to largest. So ascending order, smallest to largest. Now, the way we calculate the median depends on whether we have an even or odd number of values, right? If the number of observations is odd, it's relatively simple, right? Like if it's a small enough number of data, right? If it's small enough that you can put in an easy list and just look at it visually, right? It's the middle point, right? So if there's 5 observations, it's the third one, right? If you put 5 and you say which is the middle, it's easy to see, okay, the third one is the middle point, right? So you don't even, particularly if it's a small enough number of observations, you don't even really need a formula. It's just, you could see it visually. Oftentimes, though, we have a large enough number of observations that it may not be clear visually exactly what is the middle one. So we need a general rule for selecting the middle value. So the median, when there's an odd number, is the x value or xm value, where m is, again, is in a list of observations that are sorted smallest to largest, where m is the n plus 1 over 2 observation. So say we've got 11 observations. So m would be equal to 11 plus 1, so 12 divided by 2 would be, therefore, it'd be m is 6. And so the median would be the 6th observation when arranging from smallest to largest. So it'd be the 6th observation. And that makes sense, right? So if we've got 11 different observations and we take the 6, there are 5 that are smaller, right? If we take the 6, and then there's 7, 8, 9, 10, 11 observations that are bigger, so 5 observations that are bigger. So the 6th observation is the middle one. Again, we're turning the one where there's 5, right? And we've already seen, you could think of it just visually, the third is the middle one. Well, if we put 5 plus 1, 6, divided by 2, 3. So it would be the median is the 3rd observation when observations are arranged smallest to largest. So again, like with small enough numbers visually, you could probably figure it out, but usually that's not practical. And in tests, I don't want you doing it the visual way. I want you practicing using this because it's not going to be, in the real world, you're not usually going to have small enough number ones where you could just visually see, oh, the middle one's the third, encircle that. If the number of observations is even, the sample median takes a little bit more math. Essentially what we have to do, because if there's an even number, there's no single number that is the middle, right? If there's an odd number of observations, there's one where there's the same number of observations below and above, and we can say this one's the middle. When there's an even number, there's no single number that is the middle point. It's the middle point. It's the center of the data when arranged smallest to largest. So what we do is we take the average of the two middle points of the two that are in the center. And the way that we figure out what are the two that are in the center is, so first calculate m is equal to n plus n divided by 2. So m is equal to the number of observations divided by 2. So say we've got 10 observations. So 10 divided by 2 is 5. So m is equal to 5. And then so the median is equal to the 5th observation plus the 6th observation divided by 2. So we find the average of the 5th and the 6th observation. If there are 18, if sample size is 18, 18 divided by 2 is 9. So we take the 9th observation and we take the 10th observation, and we essentially take the average of them. We sum them up, divide by 2, we get the average. So it's the average of the middle two observations when there's an even number. And that's the median. But again, kind of thinking from this logic of the even set, we said that the median is essentially kind of the mean with the most trimming, right? So essentially in this particular case, we've dropped everything in the data set except for the two middle values, and we're calculating the average based on that. All of the other data, so we're still calculating a mean, but we've trimmed away everything except for the two middle values. So let's give this a try. So 8 grocery stores sell the PR energy bar. Again, we're returning to this. So $1.09, $1.29, $1.29. Find the median for these prices. So pause it, give it a go. Figure out which formula of the two you need to use. Calculate it out, and then resume once you've got your answer. So our formula that we have here. So there's 8 different prices. So we have to use, which is an even number. So we have to use a formula for even prices. So first step is we have to find m. And when we're dealing with an even number, m is equal to n divided by 2. So 8 observations, 8 divided by 2 is equal to 4. So then we take the 4th observation and we take the 5th observation. Here we've got the prices listed in order from smallest to largest. So we take the 4th and we take the 5th. So $1.35, $1.39, and we find the average of these two. $1.35 plus $1.39 divided by 2 is equal to $1.37. So the median here is the average of the 4th and the 5th observation. So remember we had 8. These 3 and these 3 don't go into calculating the median at all. I mean, they're important in the sense that they're smaller than this one and larger than this one, so making these two the middle values. But if any of these are outliers, it doesn't affect, right? All 3 of these could be outliers. It's not going to affect the median. All 3 of these could be outliers. 1 of them can be an outlier. 2 of them could be an outlier. It's not going to affect the median at all. So it's not sensitive, or it's as insensitive to outliers as you could pretty much get, right? So you could have several weird observations and still be fine, still have your median unaffected. But it does mean, like I said, it is dropping a lot of data, right? These aren't really factoring in. These aren't really factoring into your calculation. And so that is a sacrifice. So notice that nearly half of the n value, so half of the values can be made arbitrarily large without making the value of the sample median arbitrarily large as well. Consequently, the finite sample breakdown point is approximately 0.5, the highest possible value. So about half of the values would have to be outliers or arbitrarily large or arbitrarily small to affect the median. And that's extremely high. Like if half your data set's an outlier, then it's hard to necessarily call them outliers. So the mean and median lie at the two extremes in terms of their sensitivity outliers. The sample mean can be affected by a single outlier, but about half of the observation must be altered to make the median arbitrarily large or small. So the median is much less useful in terms of like calculating more advanced statistics. The formulas that rely on the median are more difficult to use. The median is much more difficult to interpret, like the more advanced statistics that rely on the median, and it sacrifices a lot of information. So there's a lot of things to not like about the median compared to the mean. But in terms of kind of real world practicality, in terms of sensitivity to outliers, and like I said, outliers are common, it has a lot to like about it. Now, between the mean and the median, we have other options, right? The median is doing the most level of trimming that you possibly can, essentially turning the sample size into 1 or 2, no matter how large your sample size is. So you could have like 1 million observations and you turn it down to essentially looking at 2 of them. And then the mean looks at all. Between those two, there's a lot of different levels of data that you could trim, right? Observations, small and largest, that you can drop. So one problem with the median is that it may trim too much of the data, right? Sacrifice too much. So a trim mean removes a specified proportion of both the lowest and highest values, and then it takes the average of the remaining values. So for example, if the lowest 10% and the highest 10% of the observations are removed, the average calculated is referred to as the 10% trim mean. So the 10% trim mean, if you're calculating that, you're calculating the mean, but first you're dropping the smallest 10% and the largest 10%, and you're calculating the mean based on the remaining 80% of the data. If you're doing a 20% trim mean, you're dropping the smallest 20%, you're dropping the largest 20%, and then you're calculating the mean based on the remaining 60% of the data. So it's using a lot more of the data, particularly like say the 10% mean, but even the 20% trim mean is using a lot more of the data than the median. It's still using less data than the mean. It's more sensitive to outliers than the median, less sensitive to outliers than the median. But to some statisticians, they say it hits kind of the nice compromise position, right? Yes, you're sacrificing some data, but and you have some vulnerability to outliers, but you have a lot less vulnerability to outliers compared to the mean, and you have a lot more inclusion of data compared to the median. So kind of like a nice compromise position. So it's not uncommon with more advanced statisticians to see them using things like the 10% or the 20% trim mean to protect themselves against, against outliers, and they're making assumptions that while they may have some outliers, it's not going to be more than 10% or 20% of their data on any particular side, and so it won't be affecting them. Those outliers won't be affecting them. It's a gamble, right? If you take 10% and 12% of your smallest data are outliers, you still have a problem. But so it's making some level of gamble. Unfortunately, you never know beforehand which one is best. But that's always the case when we're choosing techniques. You have to go with your best judgment. So as an example, so for we'll work through the first one together. So for the following values, calculate the 10% trimmed mean. So we've got 37, 14, 26, 17, 21, 43, 25, 6, 10, 11. So first, similar to a median, we have to put them in order from smallest to largest. Because remember, we're getting rid of some of the smallest values and some of the largest values. And so to be able to do that, we have to put them in order. And since there are 10 observations, the 10% trim mean would remove the smallest observation and the largest value, right? So there's 10 observations, we're taking off 10% from both ends. 10% of 10 is 1. So we take off the single smallest and we take off the single largest, and we have the middle 8, so 80% of the data remaining. And so in this, and then we calculate the average based on the remaining values. So in this particular case, 6 is the smallest one, 43 is the largest one. So we drop those, right? We drop those, and then we take the average of the 8 remaining. So 9, 11, 14, 17, 21, 25, 26, 37. 8 are remaining, so 8. And we'd put it as X bar T is showing that you're doing a trimmed mean. And so then the average, or the mean, the trim mean, 10% trim mean is 20 in this particular case. So let's try the 20%, but this time I want you to try. So it's the same data set. So it's the same set of numbers that we had before, 37 through 11 here. But this time, rather than doing a 10% trim mean, where in the 10% you got rid of the smallest 10% and the largest 10%, and then calculate the average off of what is remaining, let's give it a try with the 20%. So pause it, calculate what you think the answer is, and then come back when you're ready. So in this particular case, 20% of 10 is 2. So it'd be getting rid of the 2 smallest and the 2 largest. And so the 2 smallest were 6 and 9. We already had them in order from before. And then it was 37 and 43 are the 2 largest. So we get rid of those. There are 6 remaining. So the 10% trim mean, or sorry, the 20% trim mean is getting rid of the highest 20%, the lowest 20%, and then we do it off the remaining, calculate the average or the mean based off the remaining 60%. So we've got 60% of the data still left. And so the 20% trim mean is 19. Not terribly different in this case. See, the 10% trim mean was 20, the 20% trim mean was 19. That's good when they're similar, right? We're more comfortable when they end up being similar, because it gives us a little bit more confidence that whichever choice we make, there's not necessarily a wrong answer. We'd start getting a little bit nervous if, say, the 10% trim mean and the 20% trim mean varied considerably, or if the mean, the 10% trim mean, the 20% trim mean, and the median are all vastly different values. We start getting you might start getting a little bit nervous in terms of, it really matters if you choose the right one. Where when they all end up being similar, at least you could sigh, a little bit of relief, being like, whichever one you end up choosing is probably not going to matter too much. In this case, they're pretty similar. Now, this slide is just for those who are a little bit more mathematically oriented. You're never going to need this formula. So essentially, this is kind of a general rule. Say you're doing a 20% trim mean, but you could do it with any level of, it's the same rule if you're doing any number. Like, so we're using 0.2 here for 20. If you're doing a 30%, it would be 0.3. If you're doing a 10%, it would be a 0.1. If you're doing a 15, it would be a 0.15. So this is just a general rule for any level of trimming, how you'd choose how many observations to drop. And so this is a general rule. If it's something that interests you, this is the formula that you would use. In our tests, to keep things simpler, and because normally this isn't something you'd be doing by hand, this is something that a statistical software would be doing for you. To keep things simpler, if I give you a trimmed mean on a quiz or on a test, I will always make it a simple one. Like, you'd be doing like 10% of 10, or 20% of 10, or 10% of 20, or 20% of 20, where the math works out easily, right? 10% of 10 we know is 1, 10% of 20 we know is 2, and so on and so forth. So it'd be ones that are obvious to calculate, where you're not going to need a formula to figure out. Like, it'll always go in round. So you're not going to have to worry about, like, how do we round down to, do we round up? Say, 20% of a data set of number of values is like 5.6. Do we round down to 5? Do we round up to 6? I'm never going to make you make those decisions. So if it's something that interests you, you can read through this for how we do round down. So if n is equal to 49, and we're doing it 20% to mean, 20% of 49 is 9.8. We would round down to 9, and we take the smallest 9 and the highest 9. That's what you would do. But that's not something that I would ever make you calculate yourself. So you're not going to need this formula. Finally, the mode is a super simple measure of location. It's probably also the most useless in a lot of ways. Like, it doesn't give you a whole bunch of in a lot of data sets, it's not going to represent necessarily the typical value particularly well, but it is super simple, and it is a measure of location, and it's simply the most common value or group of values in a data set. So say you have 15 scores and 3 people got 75, and none of the other scores were repeated more than twice, then 75 would be the mode. It's the one that is most common. Why I say it's not necessarily the most indicative is, say you had 20 scores, right? 3 people got 50, and then each of the different scores were above 50, and the median score was like 80. The mean score was 78, but there's just 3 people who did kind of poorly, and that was the most common score, but most people actually did quite well, right? Like, we would say a mean score on a test of 78 is pretty darn good, right? So we wouldn't say, if I said, well, 50 is the typical value, you'd look, well, those are the 3 lowest scores. How's that the typical value? So the value that occurs the most frequently isn't necessarily always the best representation of the one that it would seem to be the most typical, or it wouldn't necessarily be the one that seems to represent, if we want to be, summarizing our data and conveying our data in one number. It wouldn't seem to represent the data particularly well, even though it's most common. But again, it is an existing one. So here's just kind of a summary of the mode, the median, and the mean, just for helping you. How common, how often do we use them? So how do we calculate it? How common do we use it? The mean is the most familiarly used. It's the most commonly used. It's what lay people would understand as kind of the average. When we say the average or measure of location, is the one that people would think of. It's used in a lot of different statistics. It has a lot of value. The median is fairly commonly used, so it's still something you're going to see a lot of. The mode, much less commonly used, but it is sometimes used. The mean and median always will exist in a data set. In terms of the mode, there may be no mode, one mode, or more than one mode. So there might be just no value. If every different value is distinct, then there's no value that's most common. There might be more than one mode. So say every value is distinct except 2 people got one score and another 2 people got a different score. Then you might have more than one mode. But it's also possible that there's none. Does it take every value or every observation into account? The mean does. The median does not. It only, other than counting how many observations there are. But other than that, it drops everything except for the middle one or the middle 2. And the mode, again, no, it's just taking the most common ones. Affected by outliers, yes for the mean, no for the median and the mode. And then advantages, commonly understood, works well with many statistical methods for the mean. When there may be outliers, the median is really good, and it sometimes can represent the what we think of as the average better than the mean under certain circumstances. And then advantage to the mode, most appropriate for qualitative data. That's a particular case where the mode can be useful, where the mean and median aren't particularly applicable, but the mode, what's the most common category of something, cell phone that somebody has, right? In that particular case, the mode might be useful. Finally, we want to conclude with the weighted mean. So the weighted mean is another way of calculating the mean, and it's really really similar to kind of the relative frequency method, but it's something that we see when it takes into account variations in the relative importance of data values. So when certain values are worth more than others. So again, where I say it's similar to relative frequency, you could think of it as kind of like more frequent, you could think of as a kind of another way of saying more important. But the typical way that we think of, particularly for students, we think of as weighted mean, right? So think about when we're calculating your final grade in the course, right? You got a certain grade on your quiz, you got a certain grade on your test, you got a certain grade on your lab. Imagine we had one of each. We won't want to just calculate your final grade isn't the average of those three, because your test is worth more than your quiz and your quiz is worth more than your lab set, right? So if we just added up your three scores and divided by 3, that wouldn't be taken into account that they have different values. And so the weighted mean allows us to calculate the average based on the fact that the test is worth more than the quiz, and the quiz is worth more than the lab. And so we calculate the average taking those different weights into account. So the mean becomes the sum of each data value times its weight divided by the sum of all weights. So suppose your course grade is based on 4 quizzes and 1 final exam. Each quiz counts as 15% of your final grade, and the final counts as 40%. Your quiz scores are 75, 80, 84, and 88, and your final exam score is 96. What is your overall score? So in this case, the weighted mean, right? So remember, we take the score times its weight. So go back to our formula, sum of each data value times its weight. So for each of the different data values, we have to multiply it by its weight. So we got 75, that was worth 15%, 80, that was worth 15%, 84, that was worth 15%, 88, that was worth 15%, and then 96 was your test score, so that was worth 40%. And then we divide it by the sum of the weights. So each of those different weights that we multiplied it by. So in the case often of tests, it'll add up to 100, or like course grades will add up to 100. But say you're trying to figure out how am I doing, and we've only been through part of the course. Say we've done 1 test and 2 quizzes, and there are still 2 quizzes left, right? You might want to know, okay, how am I doing so far in the course? So we would have had 40, 15, and 15. So in that case, we would divide by 70, right? The sum of 15, 15, and 40. But at the end of the course, when we're doing the final grade, it would add up in that case to 100, but it's not necessarily the case always when you're doing a weighted mean that's going to add up to 100. So we put this in, 8,745 divided by 100, 87.45, and then following the rounding rule, we'd round this to 87.5. So when you're trying to keep track of now your classes, right, you now can use this weighted mean formula to figure out how you're doing in each of your courses and keep track. So even if you don't have access to all of the, if the teacher doesn't provide kind of on Leia kind of a grade sheet available that's showing how you're doing based on the weights, this is something you can figure out. You on your course outline for all your different classes, you're going to know how much each assignment is worth. So then when you get the scores on each of these different assignments, you can use this weighted mean formula to figure out how are you doing so far in your class. And then say when you're getting later in the semester, you can figure out what do I need on so-and-so test to get a particular grade maybe that you're targeting. You'll see what you need later on to be able to get, yeah, whatever you want. So this weighted mean formula can be really useful to you on a practical basis in tracking your classes. It's not only in course grades that we use weighted means, but it's probably the one that's most applicable to all of you. All right, that's it for this time. So next time we'll continue on our descriptive stats and move on to measures of dispersion.